Software architecture principles interview questions. Let's start with the basics. What is software architecture? Simply put, it's the high-level design of a system, like a blueprint for how all the pieces fit together. It's not just about writing code. It's about making strategic decisions about the components that make up your application and how they interact. Think of designing a building. You wouldn't just start piling bricks randomly, right? You'd have a detailed plan with foundations, walls, electrical systems, and plumbing all working together. Software architecture does the same for software. It covers things like identifying the key components, defining how they relate to each other, and setting constraints to guide the design process. It also considers different levels of abstraction. You'll have a high-level overview showing the major parts, and then more detailed information about specific implementations. And why is this important? Well, good architecture leads to software that's easier to maintain, can handle increased demand as your user base grows, allows you to reuse components in other projects, and ultimately saves time and money by preventing costly rework down the line. Okay, let's talk about how applications are structured specifically, monolithic versus microservices. A monolithic architecture is like a giant block of code where everything lives together in one place. It's often easier to build and deploy initially, especially for smaller projects. However, as the application grows, it can become incredibly complex and hard to scale. Think about it, any change you make might require restarting the entire thing. Now, microservices is a completely different approach. Imagine breaking your application down into smaller, independent services that each do one specific job. They talk to each other through API like little messengers. This means you can update or scale just those individual parts without affecting everything else. It's more complex to manage overall, but it offers much greater flexibility and resilience because if one service fails, the rest of your application keeps running. Okay, so let's talk about modularity. It's a really important concept in software design. Imagine your system as being built from Lego bricks. Each brick is a module and does one specific job. These modules are designed to work together with clearly defined rules of engagement like an API so they don't rely too heavily on each other, which makes things much easier to manage, test, and even scale up later if needed. Okay, let's talk about Solid, a really important set of guidelines for designing good object-oriented software. Think of them as best practices that help you write cleaner, more adaptable code. First up is single responsibility. Each class should have only one reason to change. Then we have open/closed, meaning you can extend your code without modifying existing parts. Liskop's substitution principle ensures that if you use a subclass, it'll work exactly as expected where a base type is needed. Interface segregation says clients shouldn't be forced to implement methods they don't need. And finally, dependency inversion. High-level modules should depend on abstractions, not concrete implementations. These principles might seem complex at first, but mastering them will make your code much easier to maintain and evolve over time. Okay, let's talk about separation of concerns, a really important concept in software architecture. Basically, it means breaking down your system into distinct pieces, each responsible for one specific thing. Think of it like building with Legos. Each brick has its own job and doesn't need to understand the entire structure. We want these modules to be independent and loosely connected so that changes in one area don't accidentally break everything else. The single responsibility principle helps us achieve this. Each module should only have one reason to change, keeping things organized and manageable. Okay, let's talk about scalability. When an interviewer asks how you ensure a system can handle growing demand, don't jump to just saying we use a database. Instead, they want to see your thought process. A key strategy is statelessness, designing services that don't rely on any stored session information. This makes scaling them out horizontally much easier. Then, load balancing distributes traffic evenly across multiple instances of your service. Microservices are another powerful approach, allowing you to scale individual components based on their specific needs. Caching, like using a content delivery network or caching data within your application, can also dramatically reduce the strain on your backend. And finally, For databases, sharding is crucial, dividing your data into smaller pieces so that it's easier to manage as your system grows. Okay, so let's talk about coupling and cohesion. They are absolutely fundamental to good software architecture. Coupling is essentially how connected your different parts of the system are. High coupling means that if you change one piece, you likely have to change a lot of others, making things really complex and prone to errors. Low coupling, on the other hand, is what we want. It's about keeping modules independent so changes in one don't cascade through the entire system. Then there's cohesion. That's all about how well the elements asterisk within asterisk a single module work together. A highly cohesive module does just one thing and does it really well. A poorly cohesive module is trying to juggle too many responsibilities, which makes it harder to understand and maintain. Basically, think of coupling as how much your modules depend on each other, and cohesion as how focused they are. Okay, let's talk about security when designing software architecture. Think of it as a core element, not just something you bolt on later. We want to start with the principle of least privilege, meaning giving people and services exactly what they need, no more, no less. Then, layering in defense in depth is crucial. Think multiple safeguards that work together. Finally, it's important to design for failure securely. If something goes wrong, the system shouldn't expose vulnerabilities. When considering your architecture, things like strong authentication, validating all user input, and encrypting data are key. Separating concerns also helps by reducing potential attack areas. Okay, so let's talk about the CAP theorem. It's super important when designing distributed systems. CAP stands for consistency, availability, and partition tolerance. Consistency means everyone sees the same data at the same time, like a classic database transaction. Availability means your system stays up and running even if some parts fail. And partition tolerance just means that even if different pieces of the system can't talk to each other because of network problems, it keeps going. But here's the catch: you can only really have two of these at once. Google Maps, for example, prioritizes availability and partition tolerance, so you might see slightly delayed updates sometimes. Banks, on the other hand, prioritize consistency. They want to ensure that every transaction is handled correctly. Understanding this trade-off is key to making smart architectural decisions. Okay, let's talk about API versioning. It's a really important aspect of building robust and scalable systems, especially as they grow. The basic idea is that you need a way to manage changes to your API without breaking things for existing users. There are several ways to do this. You could just add versions to the URL like /API/phone/users, which is straightforward but can lead to really long URL. Another option is using headers, like accept application/vnd mycompany API, phone plus JSON. This is more flexible. For very complex systems, you might use content negotiation through the accept header that requires more client-side work but offers the most flexibility. As your system grows, always think about backward compatibility. New versions shouldn't break older clients unless absolutely necessary. It's also crucial to have a clear deprecation policy and manage database schema changes carefully. Feature flags can be super helpful for rolling out new features gradually. Okay, let's talk about why you might want to use message queues in your software architecture. Basically, they are a fantastic way to make your systems more flexible and resilient. They decouple different parts of your application. Think of one server sending a message without needing to wait for another to respond immediately. This is great for asynchronous processing, which means things can happen behind the scenes without blocking other operations. It also helps you scale things up or down independently and provides a safety net by buffering traffic when loads spike. Most importantly, they make sure messages get delivered reliably. Okay, let's talk about caching. A really common question in software architecture interviews: how would you implement it? The key is to think about a layered approach. First, we always want to leverage the browser's own cache for things like images and CSS. That's super fast. Then, CDN can help distribute content closer to users around the world. Next up, a reverse proxy like Varnish or Nginx can sit in front of your web server and quickly serve cached responses. Finally, within your application itself. You might use something like Redis or Memcache to cache frequently accessed data, maybe results from complex calculations. But don't forget about invalidation. How do you make sure your cache isn't serving stale information? You'll need a strategy for things like TTL, time to live, and potentially invalidating the cache when content changes. Let's talk about middleware. It's a really important concept in software architecture. Essentially, it's like the middleman between your applications and everything else: databases, other services, you name it. It simplifies things by handling all the messy details of communication, so each app doesn't have to know exactly how every other system works. This makes development much easier and helps ensure that different parts of your system can work together smoothly and reliably, even if they're built with completely different technologies. Okay, let's talk about layered architecture. It's a really common and valuable pattern in software design. Basically, we separate our application into distinct sections like building blocks that each have a specific job. We typically have layers for the user interface, where users interact with the app, then a business logic layer containing all the rules and processes, a data access layer which handles talking to databases, and finally, an infrastructure layer providing essential services like logging and security. The key is that each layer only communicates directly with the layers right above or below it. That keeps things organized, makes it easier to maintain and test your code, and allows you to scale different parts of your application independently. Okay, so let's dive into design patterns. Essentially, they are like tried and true solutions to common problems in software development. They aren't just code snippets, they are more like blueprints, descriptions of how to tackle those challenges effectively. We have some classics like the singleton pattern for ensuring only one instance of something exists, or a factory pattern that lets you create objects without specifying exactly what kind. Observer is fantastic for handling events, and strategy allows you to swap algorithms easily. You should use them when you're facing repeated problems, want your code to be easier to understand and maintain, or need a design that's flexible and can grow with your project. But remember, don't force them in. Focus on good design principles first. Okay, so this question is all about thinking strategically. We're asked to design a system for real-time data. Think things like sensor readings, financial transactions, or website activity. The first thing I'd do is acknowledge the core challenges. We need it to scale as the data grows, be fast enough to deliver results quickly, low latency, and be robust in case something goes wrong. My go-to approach is a microservices architecture. This breaks down the system into smaller, independent services like an ingestion service that pulls data in, a stream processing service that actually does the work on it, and then a storage layer to hold the results. The specific technologies would depend on the exact requirements, but Flink or Spark streaming are common choices for the stream processor, and NoSQL databases are often great for handling large volumes of data. Okay, let's talk about scaling. How do we handle increased demand for our applications? We'll start with vertical scaling, which is basically just making existing servers bigger and stronger. It's relatively simple to set up initially, but there are limits to what you can achieve, and if one server goes down, the whole system could be affected. Then we have horizontal scaling, where we add more servers to share the workload. This is much more scalable and resilient. If one fails, others pick up the slack. However, it's a bit more complex to implement. Okay, let's talk about choosing between SQL and NoSQL databases. It's a really common interview question. The key thing to remember is there isn't one better choice. It all depends on your specific project. SQL databases are like well-organized spreadsheets. They have a strict structure and are great for things that need strong consistency, like handling money or orders. NoSQL databases, on the other hand, are more flexible, like storing documents in different formats. They're fantastic when you're dealing with lots of different kinds of data, and scaling up quickly is important. Think about it. If your application needs to handle a huge number of users posting updates constantly, NoSQL might be a better fit. So, really think about the structure of your data, how you plan to query it, and how much scale you need. Okay, let's talk about dependency injection. It's a really important concept for building robust software. Essentially, instead of a class creating its own dependencies directly, we give those dependencies to the class. Think of it like this: you're not building the tires yourself, someone else provides them. There are different ways to do it, like passing in dependencies through the constructor or using setter methods. The key benefit is that DI makes testing way easier because we can swap out real dependencies with mock versions. It also leads to more reusable code and reduces how tightly classes are connected, making your whole application much more flexible and simpler to maintain. Okay, let's talk about transactions in the wild, specifically when they span multiple services. It's a really common interview question because distributed systems can be incredibly complex to manage consistency across them. The core challenge is that each service might have its own database and logging system, making it hard to guarantee those traditional ACID properties we're familiar with. One popular approach is the Sugar pattern. Think of it like a choreographed series of local transactions. Each service does its job, and if one fails, we roll back everything that came before and then run compensating transactions to undo any changes. Another option, though often more complicated, is two-phase commit. However, be aware that these patterns frequently lead to eventual consistency, meaning data might not always be instantly consistent across all services, but will eventually synchronize. It's crucial to consider idempotency when designing compensating transactions and monitor your system closely, as distributed transactions can introduce significant complexity. Okay, let's talk about a really important architectural decision. How do we get different parts of our system to communicate with each other? We have two main approaches here: synchronous and asynchronous communication. Synchronous is like a phone call. Both sides need to be available at the same time. It's simple and gives you immediate feedback, making debugging easier. But it can cause a bottleneck because one side has to wait for the other. Now, asynchronous communication is more like sending an email. You don't have to wait for a reply right away. This lets multiple things happen at once, which is great for scalability in building systems that can handle lots of requests. However, it's also more complex to set up because you need tools like message queues to manage the communication. Okay, let's talk about logging and monitoring, a really important part of building reliable systems. It's not just about slapping some logs everywhere, it's about having a thoughtful strategy. First, you need to choose the right tools for the job, like ELK or Graylog for centralized logging and Prometheus or Grafana for metrics. Then use different log levels: debug, info, warning, error, fatal, so you're not drowning in unnecessary information in production. And vitally important, always include correlation ID to trace requests across your system. Think about the key things you want to measure. Response times and error rates are good starting points. Then actually add logging statements to your code where it makes sense, and set up dashboards to visualize those metrics and alerts so you're immediately notified of any issues. Okay, let's talk about how we'd approach breaking down a large application into smaller pieces. First and foremost, it's crucial to really understand what the whole system does. We want to identify those areas called bounded contexts where different parts of the application have their own distinct responsibilities and data. Then, instead of trying to overhaul everything at once, we should prioritize starting with some smaller, less connected modules. Think about workflows like how a customer places an order or searches for a product. Once we've identified those areas, we need to clearly define the boundaries of each microservice, what it owns and what it's responsible for. Finally, we need to think about how these services will talk to each other, choosing the best communication methods like REST API or message queues. Okay, let's talk about domain-driven design. Essentially, it's all about understanding the business you're building software for. Instead of just focusing on technical details, DDD forces us to really dig into what the company does and how they do it. It's like creating a detailed map of the world, ensuring everyone, developers and business experts alike, uses the same language when describing it. We'll focus on things like the ubiquitous language, a shared vocabulary between everyone involved, and bounded contexts, which are essentially defined areas with their own specialized models. It's not just about creating technically sound code, It's about ensuring that your software truly reflects and solves the real-world problems of the business. Okay, let's talk about managing configurations in distributed systems. It's a really important topic for any architect. Think of it this way: when you have multiple services talking to each other, they all need to know how to behave, right? That means knowing things like database URL, API addresses, basically their settings. It's a big challenge because those settings can change, and keeping them consistent across all your services is key. There are several ways to do it. Simple things like environment variables work okay for small setups, but centralized tools like Console or Act are generally better for larger systems. And don't forget about secrets management. Storing passwords and API keys securely is absolutely vital. A good strategy is to treat your configuration as if it were code, meaning you version control it, and make sure services can update the settings without having to restart. Okay, let's talk about the circuit breaker pattern. It's a really clever way to build more resilient systems. Imagine an electrical circuit breaker in your house. It protects you from getting an electric shock if something goes wrong with the wiring. This pattern does something similar for your software applications. Basically, when a service starts failing repeatedly, the circuit breaker trips and stops sending requests to that service. This prevents a domino effect where one failure causes others to fail as well. It then waits a bit, checks if the service has recovered, and only sends requests again once it's confident the service is back online. It's all about protecting your applications from overwhelming problems. Think of it like a safety valve. Let's dive into the proxy pattern, a really useful design principle in software architecture. Imagine you have an important object, let's say a database connection. The proxy acts like a gatekeeper for that connection. It doesn't do anything with the data itself, it just manages how other parts of your application interact with it. This allows us to add extra features like logging every time someone accesses the database, or even caching frequently used information to speed things up. It's incredibly useful when dealing with remote resources or situations where you need fine-grained control over access. Think of security checks or ensuring everything is properly logged for debugging. It's all about adding functionality without directly modifying the original object. Okay, let's talk about REST versus GraphQL, a common interview question. Essentially, REST uses multiple endpoints, each returning a fixed set of data. Think of it like ordering food at a restaurant with separate menus for appetizers, entrees, and desserts. However, this can lead to overfetching, getting more data than you need, or underfetching, not getting enough. GraphQL flips the script. It's all centered around one endpoint, and the client asks exactly what data they need. This is super helpful when your clients have different needs, like a mobile app needing a smaller payload compared to a web dashboard. REST is generally easier to get started with if you're building something simple quickly, but GraphQL can be a game changer for performance and flexibility as your application grows. Okay, let's talk about event sourcing. It's a really cool pattern that shifts how we think about storing data in our applications. Instead of keeping a snapshot of the current state like customer has this address, we focus on recording every single thing that changes. We record these changes as events, kind of like transactions in an accounting system. Each event describes what happened, not how it happened. It's fantastic for understanding exactly what went down over time and building a really robust audit trail. And because we're just tracking events, it opens up the possibility to rebuild state at any point, which is super powerful for debugging or recreating past scenarios. Okay, so let's talk about the repository pattern. It's a really common question in architecture interviews, and for good reason. Basically, it's like creating a central point of contact between your application's business logic and where the data actually lives, whether that's a database or an API. The key benefit is decoupling. It means your core code isn't directly tied to how the data is stored, making things much easier to test and maintain. Think of it as a data hub that handles all the data access for you. Okay, let's talk about securing our microservices. It's vital that services trust each other and aren't vulnerable. One really important strategy is mutual TLS. Essentially, each service proves its identity to the others with digital certificates. Think of it like a secure handshake. We also use API gateways to act as a gatekeeper, making sure only authorized services can talk to each other, along with authentication mechanisms like JWT. Service meshes take this a step further by automating much of the security process, including MTLS and traffic control. And don't forget simple things like validating all data coming in to prevent common attacks. Okay, so let's talk about shared nothing architecture. Essentially, it's like having a bunch of completely independent computers working together. They don't share any memory or processing power directly with each other. Instead, they communicate through messages. This makes the system incredibly scalable because you can just add more computers to handle increased load, and it's also pretty resilient to failures. If one computer goes down, the others keep running. It's a really common pattern in modern large applications like microservices. Okay, let's talk about idempotency, a really important idea when designing systems that need to be reliable and handle failures gracefully. Essentially, an operation is idempotent if you can run it multiple times without changing the final state of things. Imagine clicking a like button on social media. One click adds a like, but 2 clicks shouldn't add another. It's vital for making sure systems don't get into trouble when messages are delayed or retried due to network issues. Think about how it helps with fault tolerance. We can achieve idempotency by using unique identifiers for requests, keeping track of what's already been done, or even building in checks so we only perform an action if it hasn't happened before. Okay, let's talk about how we tackle state when things are spread out across multiple computers in a distributed system. It's actually quite tricky. The big challenge is getting everyone on the same page, ensuring data consistency. We don't always need immediate accuracy, so we often lean towards eventual consistency, where updates eventually sync up but might not be instantly reflected everywhere. Another common technique is CQRS, which separates how we write and read data, allowing us to optimize each for its specific purpose. Sagas are like choreographed sequences of operations that make sure things work out in the end, even if there's a hiccup. And finally, idempotency, designing our actions so they can be safely repeated without changing the outcome, is super important for reliability. Let's talk about bounded context. They're really important for building robust software architectures. Imagine your company is tackling a big project like an e-commerce website. Instead of trying to build one giant database that handles everything you'll likely find that different parts of the system need their own specialized models and rules. A bounded context essentially defines those independent areas like order processing, customer management, or product details. Each of these has its own unique data structure and logic, completely separate from the others. This approach makes things much more manageable, reduces complexity, and allows you to scale your application effectively. Okay, let's talk about rate limiting, a really important concept in building robust applications. Essentially, it's all about controlling how many requests a user or client can make to your service within a certain time frame. There are several ways to implement this, like the token bucket and leaky bucket algorithms, each with its own strengths. The key is to consider things like granularity. Should we limit by individual users, IP addresses, or something else? Also think about the window size, balancing accuracy with responsiveness. And finally, decide if you want a centralized rate limiter, which is easier but can be a bottleneck, or a distributed one for better scalability. Okay, so when you're asked about anti-patterns in architecture, it's really about recognizing those common design mistakes. Basically, they're bad practices that show up repeatedly like a well-worn path to trouble. We've got some key examples. God objects, which are classes trying to do everything leading to difficulty with testing and organization. Then there's spaghetti code, where the code is just tangled. Copy-pasting, where you duplicate code instead of building reusable components, and even a big ball of mud, a system without any real structure. Finally, we have feature factories, which are classes that create things for other classes without really understanding what they need. Spotting these can save you lot of headaches later on. Okay, let's tackle a really common interview question. How do you approach prioritizing non-functional requirements? These aren't just about what your software does, but how well it does it things like speed, security, and scalability. It can be challenging because these requirements are often vague to start with. A great way to tackle this is using the MOSCOW method, which stands for must have, should have, could have, and won't have this time. Must-haves are absolutely critical. Without them, the project just won't work. Should-havens are important but not essential, and we should aim to include them if possible. Could-havens are desirable additions, but aren't vital. And finally, won't-havens are things that are outside of this particular release. The key is getting input from everyone involved: stakeholders, developers, testers, and even users. Then, you need to consider the cost versus benefit of each requirement and assess any potential risks. Okay, let's talk about CQRS command query responsibility segregation. Essentially, it's a clever way to manage how your application interacts with its data. Think of it like this: traditionally, we treat reading and writing as one big process, which can cause problems when things get complex or you have lots of updates. CQRS breaks that up. It separates the operation of commands change the data, while queries just read it. This allows each side to be optimized for its specific task, leading to better performance and making your application much easier to scale. It's all about eventual consistency. Don't worry if things aren't perfectly synchronized right away, it'll get there eventually. Okay, let's dive into designing a multi-tenant application, a really common question in software architecture interviews. The main challenge is figuring out how to share infrastructure while still keeping each customer's data and resources separate. There are several approaches you could take: a shared database with different schemas for each tenant, a pooled schema where all tenants use the same schema but are identified by an ID, or completely separate databases for each tenant, which offers the most isolation but is also the most complex to manage. When designing this kind of system, it's crucial to think about how you'll identify the tenant in every request, how you'll ensure data isolation, and how you'll allocate resources fairly across all your customers. And finally, good monitoring and reporting are essential for understanding how things are running. Let's dive into design spikes. Basically, it's a short burst of focused work, usually just a day or two, where you tackle a tricky technical question. Imagine you're not sure if a certain architectural pattern is going to work for your project. A spike lets you quickly build a little prototype and test it out. It's about proving things out, not building a finished product. They are super helpful when you're facing uncertainty or need to validate an idea before investing heavily in a solution. Just remember, they're a tool for exploration, not the final answer. Okay, let's talk about orchestration and choreography. They're both ways to manage a bunch of independent microservices. Think of orchestration like having a conductor for an orchestra. The orchestrator tells each musician exactly what to do and when. It's great for complex workflows with many steps, but if that conductor messes up, everything stops. Choreography, on the other hand, is more like a dance party. Each service listens for specific signals, events, and just reacts to them. They don't need to know what anyone else is doing. This makes things more resilient because if one dancer stumbles, it doesn't necessarily ruin the whole performance. It's a trade-off. Orchestration can be simpler to manage initially, but choreography offers greater independence and fault tolerance. Okay, so when interviewers ask about future-proofing an architecture, they're really probing how adaptable you are. The key is to move away from monolithic designs and embrace modularity, breaking your system into smaller, independent pieces. Think microservices. Next, prioritize API. Clear interfaces allow components to change without breaking things. An event-driven approach further strengthens decoupling. And crucially, avoid getting locked into a specific technology. Design with flexibility in mind so you can easily adapt as new technologies emerge and user needs shift. It's about anticipating the future, not just building what's needed today. Okay, let's dive into service registries. They're super important when you're building microservices because they solve a really common problem: figuring out where your services are located and how to talk to them. Basically, it's like a phone book for your applications. Every service registers itself with the registry, telling it its address. This allows other services to find each other dynamically without needing to be hard-coded. As you add or remove services, the registry keeps everything up to date, making scaling and handling failures much easier. It's all about loose coupling and creating a flexible system. Okay, let's talk about handling failures in a distributed system. It's a really important area for architects to be familiar with. Basically, because these systems are made up of many different pieces working together, things will go wrong sometimes. So, we need to build them to be resilient. That means thinking about fault tolerance. How can the system keep going even if parts fail? Redundancy is key. Having backups and duplicates helps a lot. Then there are circuit breakers, which stop requests from failing services before they cause more problems, and retries with careful backoff in case something is just temporarily unavailable. Also, consider things like idempotency, making sure operations can be done multiple times safely. And finally, explore strategies like eventual consistency or using quorum consensus to ensure data remains reliable even if nodes go down. A good approach isn't just knowing the concepts, it's being able to describe how you would apply them in a real situation. Okay, let's talk about designing a system that can stay up and running no matter what. A really common interview question is, how would you design a highly available system? The first thing to think about is redundancy, having multiple copies of your key components. This could be web servers, application logic servers, or even database instances. We'll often use load balancers to distribute traffic and make sure no single server gets overloaded. It's important to have redundant components, but also fault tolerance so that if something does fail, the system can automatically recover without a major outage. Monitoring is absolutely critical. You need ways to detect problems early on, so we'll want robust alerting systems in place. And finally, automation. Automating recovery processes and scaling ensures things happen quickly and efficiently. Let's look at a simplified example of 3-tier architecture with presentation, application logic, and data storage tiers, highlighting how redundancy works across each layer. So let's dive into load balancing. Think of it like a traffic controller for your application. Instead of having all the requests hit one server and potentially bog it down, a load balancer steps in to distribute them across multiple servers. This keeps things running smoothly even when there's a big rush, basically preventing those frustrating waits. It's also super smart because it constantly checks if each server is healthy and will automatically reroute traffic away from any problems. And best of all, it helps you scale your application up or down easily and ensures that if one server goes down, others can pick up the slack. Okay, let's talk about the strangler pattern. It's a really clever way to tackle those massive, monolithic applications that can be so hard to maintain and evolve. Basically, you don't just rip out the whole thing and replace it, which would be chaos. Instead, you start by picking a small piece of functionality, build a new microservice around it, and then slowly route requests for that function through the new service while continuing to serve it from the old system. You keep repeating this process until everything's been replaced. It's like gently strangling the monolith with smaller, independent services, reducing risk and allowing you to deliver value faster. Okay, let's dive into eventual consistency. It's a really important idea when designing distributed systems. Essentially, it means that if you make a change in one part of the system, it will eventually spread to every other part, but there's no specific timeline for when that happened. Think about Google Docs. Both users can see changes almost instantly, even though sometimes there's a brief delay. It's great when you need high availability and don't mind if data is occasionally stale. But it definitely isn't the right choice for things like banking transactions, where you absolutely need immediate accuracy. Okay, let's dive into gateways and microservices. Essentially, they are like a single entry point for your entire system from an external perspective. They handle all incoming traffic and smartly forward it to the right microservice based on what's being requested. This simplifies things for clients because they don't have to manage multiple service addresses directly. Gateways also offer a lot of flexibility. You can change routing rules, translate between different protocols, and crucially, implement security measures like authentication and authorization in one central location, which is huge for managing complexity. Thank you for watching.